where you can see my screen, right?
Yes.
Yeah.
Mhm. Hmm, let's go on psychology. So this chapter, this section is all about uh, the classical versus the classical theory in psychology versus the reinforcement learning part of application uh, from the viewpoint of the text in the book, from the sections first and second that we have studied. So they are trying to combine both and kind of systemize the tasks, returns, and algorithms in a way that it makes a holistic sense to to a holistic sense to us, so that the learning behavior, the animal learning behavior, I think so. There are more than six or seven different animals uh, which they have experimented with in this complete chapter. So I will try to give a quick overview about the chapter first. In the initial part of the chapter, the author gives a brief description between the correspondence of reinforcement learning and the learning theories, uh, like the psychological learning theories in animals like rats, pigeons, rabbits, cats, and dogs. Uh, they are trying to uh, probe, experimentally probe the subtle properties of the animal learning, and which is and trying to answer the theoretical questions posed by them, uh, so which is related to reasoning, thoughts, animal learning experiments, and uh, cognitive processes of those particular animals, how they relate to the learning principles that we have classically established. Also, they also discuss about the connections and the connections between the classical theories versus the reinforcement learning. The classical or the Pavlovian, the conditioning and instrumentation or operant, the conditioning part of it, from the prediction and control algorithms which we have studied in the second the part of this book. Mm, so here in the section 14.1, prediction and control, they give us a broad overview about the prediction and the control part. with the psychological with the psychology's influence on the reinforcement learning, uh, they kind of like define prediction algorithms uh, in terms of how an agent in environment here, the agent can be one of the animals that we had discussed earlier, how of that animal is expected to unfold over the future. Hmm, future with respect to the how the interaction with the environment results in the uh, what sort of a future rewards we give to those particular agents, and what are the correspondences between the reinforcement part and the stimuli, the agent part of them. Uh, they also talk about the conditioning experiments, instrumentational or the operands, and conditioning part of the agents to uh, set up a typical behavior of a particular agent in a particular environment by giving a reward or a penalty to it. Uh, then they define a reinforcing stimulus that is set to contingent on the animal behavior, whereas in classical conditioning it is not. Then they give an overview about which laws are taken into account here. Thorndike's laws of effect. Uh, then the control part, which we will be going through uh, in this chapter. The classical conditioning, the Pavlovian control, and they also talk about the stimulus in terms of how in psychology the reinforcement is used for both the classical and instrumental conditioning. Here, the instrumental conditioning refers to, in basic, in layman terms, refers to the conditioning by which your behavior and agent's behavior is rewarded based on the particular uh, puzzle or a particular cage that it comes out of. It tries to solve that. For example, a cat can be given a puzzle to come out of a cage by which has uh, three or four different ways to uh, 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 open up a cage, and if that particular cat follows a sequence of steps, these three or four steps, then it will be free So that's a kind of instrumentation that they are referring to, is instrumentational conditioning. You know, what's the an animal behavior on that particular stimulus. Then we come to the section 14.2 classical conditioning. The We study the digestive system of the activity of a digestive system in the PAB, in the Russian physiologist Ivan Pavlov, whose who gave a theory of the animal's innate responses to certain triggering stimuli, and how are they trainable with respect to the other inborn triggers that a animal has. So we give an example of the salivation here, of uh, when the food, in one of the cases, uh, the dogs had undergone a minor surgery to allow for the intensity of this salivatory reflex to be accurately measured. So that dog had gone through a minor surgery, and in one case, he describes a dog that does not salivate under the most circumstances, the most circumstances, but about 5 seconds after being presented with the food. So that is one of the examples of how he worked on his test subjects. Uh, After several repetitions, they presented with the he was presented. They presented his agent with another stimulus, which is not related to food, and the sound of a metronome, uh, shortly before the introduction of food, and the dog salivated res- in response to the sound of the metronome in the same way as it did to food. So that activity of salivary gland has just been called into play by the impulses of sound, which is a stimulus was quite alien to food. And then he wrote uh, was his paper on this. Then there are a bunch of uh, 4 to 6. There are uh, short abbreviations that we need to learn here. I'll try to read through this paragraph. This paragraph is very important, uh, in which Pavlov called the inborn responses unconditioned, unconditioned responses, the URs. That is example the salvation in this demonstration described above. So that was the unconditioned responses, the URs. So we will have to remember this. UR means unconditional responses, and it refers to the salvation of how they did it. The unconditional stimuli, the natural triggering stimuli, of example, the food, the conditional, the conditioned responses. Here also the salvation and the conditioned stimuli, the metronome sound. So these four unconditioned responses, unconditioned stimuli, conditioned responses, and conditioned stimuli. Conditioned responses and conditioned stimuli are with respect to the metronome sound and the metronomes sound, the salvation due to metronome sound, uh, unconditioned response and the unconditional stimuli is the normal uh, behavior that is expected of a particular agent. Then they talk about delay conditioning between the CS conditioned stimulus and the US, the unconditioned stimulus. So here you can see uh, then the delay conditioning, the CS extends throughout the interstimulus interval or the ISI, which is the time interval between the CS onset and the US onset. So that's the time here, ISI, with the CS ending in the US, the common version is shown here. And in trace conditioning, the US begins after the CS ends, and the ISI is still the offset, the time offset here. So that's the difference between the delay and the trace conditioning. And then they discuss this. Uh, the differences, the experiences and salvation of the Pavlov, Pavlov's dog. Uh, and they discuss more cases of the examples and the differences between the different uh, stimuli and the unconditional and the conditioned responses. Here they talk about the rabbit's eye triggering uh, closure of the productive inner eyelid called the nictitating membrane. Uh, when a puff of air is blown into a rabbit, blown into a rabbit's eye. So, uh, then they talk about the CRs being initiated in anticipation of the air puff and appropriately timed. buffer for the better protection is simply initiating closure as the reaction to the irritating US, and the ability to anticipate the important events by learning the predictive relationships among the stimuli so that it is beneficial to the presence of the animal kingdom. So that's the classical way of how the unconditional response gives in with respect to the unconditioned stimuli. So they talk about this in this uh, paragraph. Then the 14.2.1 is blocking and the higher order conditioning. And so these are the conditioning properties that have been observed in the experiment. Uh, Blocking occurs when an animal fails to learn a CR, the conditional response when a potential conditional stimulus is presented along with another conditional stimulus that had been previously used to condition the animal to produce that CR. So when the animal fails to learn this, then it's called a blocking. And higher order conditioning occurs when the previously conditioned CS acts as a unconditional stimuli in conditioning another internally uh, in conditioning another initially neural stimulus. They talk about this here. The second order conditioning, metronome that was not followed by food. Then they give an example of a black square uh, in which the stage of the conditioning was the sound of the metronome and then the prediction of US food. Number of trials conducted in which the brass the black square was placed in the dog's line of vision following the sound of the metronome, and it was not followed by food. So, in just 10 tries, the dog began to salivate merely upon seeing the black square, despite the fact that the sign of it has never been followed by the food. So, that's the second order conditioning, or from the higher orders of conditioning, in which the conditioned stimulus is being used to train another conditioned stimulus. Then they discuss about the other parts of it here, such as the intermixing of the first order trials with the higher order trials, or by providing a general energizing stimulus beyond the second order. Uh, so this is difficult to uh, bootstrap or implement in a particular uh, agent. So yeah, yeah. So this is the higher order instrumental conditioning that they have uh, experimented with. They discuss this in these two paragraphs too. Then we come to the Frescola Wagner model, which was mainly developed to account for blocking. Yeah, this is a bit. I think so. They discuss here uh, associative strength and the emotional aspects of that. Yeah, they discuss about the associative strengths of the component of each of the components that is stimulus of a compound of CS. And this is difficult. This is a bit difficult stuff. I didn't get most of the things, but anyway, let's look at the equations here. Here VA, VX, and V of AX denote the associative strengths of the stimuli AX and the compound AX. And the compound CS AX is followed by a US, the unconditioned stimulus, which with the label Y, and alpha A and beta Y. Alpha X, beta Y are the step size parameters here. Uh, V of A plus V of X. Ah, I think so. That's the key assumption of a model, that the aggregate associative strength V of X is equals to V of X, V of A plus V of X, and they are changed by deltas, become the associative strengths at the beginning of the next trial. Okay, so they are given here two equations. These are the associative strengths at the beginning of the next trial. Uh, the stimulus component change according to these expressions. Uh, these are the mapping of V's to the CRs, conditional response. Then so this also explain blocking in a sense. That stimulus compounded the asymptotic levels of the associative strength. That's Ry and the US of Y, which can support it. The prediction errors Ry minus the V of Ax is positive. So, yep. Yeah, so this is all that stuff. Uh, Anything you guys want to add to this? So I'm just reading the equations here, trying to understand trying to make sense of what they have.
Yeah, so this model, although it's kind of classic, it seems to be outdated, right? So it
Mhm.
does account for blocking, but it doesn't account, unlike the TD model that we will discuss next, for the higher order conditioning. And here, basically what it says, so we are trying to explain this phenomena that when we add, so we have a conditioning on stimulus A, and then we add another stimulus X, which only comes with A, and therefore it does not have any, like it does not add to this cumulative or aggregated associative strands VAX, right? So because V of A is just as the A itself is just as strong evidence as A plus X, and that is why we do not learn. So we do not create this conditional response based on X in this case. So yeah, I guess that's interesting that our mind is kind of works in this way, that we are trying to learn all of the available information, right? But also we don't want to learn any kind of stuff that does not add. So yeah, if you think about it like from information theoretic perspective, the fact that this new stimulus that is added, uh, the second stimulus X, it does not kind of decrease our entropy of the world, because it is like A plus X is no more predictive than A alone, right? And this model was, I believe, constructed um, to explain that phenomena. But yeah, on the other hand, judging from what comes next, this model is not kind of a true model of the processes that occur in our brains, just some kind of a step toward understanding what's going on, right?
Yep. True, true.
Yeah, and here, so they kind of relate this two things, the value functions that we learn in reinforcement learning, and this like predictive power of stimulus, or predictive effect of stimulus. And I guess the process that we use uh, to learn a value function in reinforcement learning is very similar to that in what in psychology is used to describe this Pavlovian conditioning. And that's interesting. I wonder if basically, so I believe the intuitions that stand behind reinforcement learning come from psychology, right? But I wonder if it's possible even to diverge from this, or basically the way our learning works is also maybe the only way we can achieve a similar kind of result, what we want to do in reinforcement learning, essentially.
Essentially, it's the same what they're trying to do, but yeah, uh, the theories that correspond here are they're just talking about blocking here. So yeah, keep that in mind when going through this uh, the Rescorla Wagner model. Maybe I'm stopping my share. You can continue with Arto. Maybe you can continue with your.
Yeah, okay. Yeah,
Uh,
I'll try. Although I'm not quite like, yeah, I don't have like deep understanding of the topic as well, but so yeah, we discussed this uh, Rescorla Wagner model, and essentially that's kind of, you can see how it relates to value function learning. And next, but also one of the problems of this model is that it does not um, it does not explain the higher order conditioning, and also it treats the learning like an experiment by experiment process, so episodic kind of process. But actually, what we observe in reality is more like a real-time process. And to explain those kinds of processes is a more kind of a bit more complex and elaborated TD model was designed, and it's a real-time model, yeah, as opposed to this trial level model. And the idea here is like let me scroll to this. Okay, so there are different ways to represent the stimuli observed or observed during experiment, and we can kind of see these three ways to represent stimuli. And you can think of this representation as a feature vector. And you can see that there are the simplest one is a presence. So you can think of it as a binary feature, if stimuli is present or not. And you can see some more complex representations that, for example, this complete serial compound representation kind of divides this time interval into parts and construct different features, which allows us to represent the stimuli more precisely with respect to the duration of it. And there is this microstimuli representation that is even more complex, and there are a bunch of features that correspond to so they have different intensity at different time of stimuli presence, and that's more so this is believed to be more relevant to the real processes occurring in mind, but still all these representations allow us to learn effectively this conditional responses. And a way to explain it would be very similar to the eligibility traces idea. So what we do here, we treat our experiment as a as a flow of time, and we so here they say let's arbitrarily decide, for example, the time resolution to be 1/100th of a second, and probably there is some kind of way to find a grounded number that relates to our physiology, so how on which kind of time resolution we operate. And then we can essentially, what we can do, we can treat the stimuli as a set of features. So we will represent kind of our current situation with a set of features X, and each feature would be kind of will be corresponding to if this stimuli is present or not. And then we can also introduce this idea of eligibility trace. And so you can think of it as once we observe a stimuli, we keep it in mind for some time. So you heard a sound, and then you kind of still keep the association with this with that sound active. And if some outcome, so for example, unconditional stimuli occurs in after the sound, we will associate the sound with this unconditional stimuli. So this model, as you can see, it just the same as temporal difference learning with eligibility traces, right? So in this case, a prediction error, you can think of it, and or TD error would be like the reward here is not necessarily a reward. It might be just something which is an unconditional, so some reactions that we have in our organisms to unconditional stimuli, and then we will represent this our perception of what's going on as a value function with a feature vector that corresponds to this kind of stimuli we observed recently, and we will update the basically our reaction to the stimuli according to this formula, which is the same as the semi-gradient TD with eligibility traces update. And so the notations here should be familiar. We have this discount factor gamma and eligibility trace decay lambda. And I believe somewhere in the book they briefly mentioned that there are more and probably what's actually going on in our brains is more complex than just an exponential decay. But maybe that will be covered in the neuroscience chapter, or yeah, actually that's kind of interesting if a more complex eligibility trace is beneficial, or maybe it's even kind of necessary in a more complex environment. So like a world we live in. All right, so now let's look to the kind of what this model allows us to represent. And here we will discuss this higher order conditioning. So we have two stimuli, A and B. So let's see here. So we have this conditional stimuli A followed by conditional stimuli B, and then we have unconditional stimuli after that. And here you can see how kind of the conditioning on A is much stronger when B is present. So B is, I believe, in this experiment, the B was intermediate stimuli that was strongly associated with unconditional stimuli, and then A was introduced, so another stimuli that comes before B, right? Let me see. And then we can apply this TD model and observe this W can be thought of as a strength of association, right? So that's kind of weight. All right, and then we have another experiment that shows us this blocking phenomenon. So here, in the previous experiment, we first associated B with the unconditional stimuli and then added A. And in the next experiment, we first associated A with unconditional stimuli, and then we add B. So here you can see that A is present, then B comes in, and you can see that the association strengths corresponding to B becomes kind of smaller, is diminished as the association with A becomes stronger. So that looks to me, I think, like it kind of overrides the conditioning on B by conditioning on A in this case. So here you can see we start with a high weight on B, and if we as we do trials, if A is absent, the B remains strongly associated with the response, and if we introduce A as the time goes on, the association with B becomes weaker, and that's because this A is, I think, a stronger predictor in this case, because it starts earlier, right? And yeah, and in this case, it was kind of similar experiment, but here we had no association with B at the beginning, unlike in the next experiment. But you can see the same kind of phenomena, that if we have stimulus or stimuli A, then B is gets much weaker association. So that's blocking. And yeah, and this first experiment is illustration of higher order conditioning. So here we associate A with S by means of intermediate stimuli B. Right. So and does it make sense? Do you can agree with what I take off from it, or would you like to add anything to this?
It makes sense.
All right. And here we see, okay, so here we see the second order conditioning. We have a strongly associated stimuli B in the beginning, and then we add A, and it is and we do not have any unconditional stimuli here. So you can see as the association of B kind of decays, but also you can see that although A was never observed together with unconditional stimuli, it gets some association because of it is present before B. But later, when we kind of decrease the weight of B as predictor of the unconditional stimuli, we also decrease the weight of A. So this model seems to be a better description of what's of the observed experimental data. Yeah, and people are studying this kind of responses in our brain and trying to explain it, but still this is kind of you can think of these models, I guess, as approximations to describe what's going on. So if you want some kind of analogy, I guess that would be like I don't know, like a Newtonian theory of gravity. It does not kind of describe the true reality of physics, but it is a good approximation to explain the observed phenomena. And yeah, so that's at least how I understood this kind of models. So, and the way to reason about it. Yeah, and there are this comparison of different feature representation, and you can see that using different kind of representation, we observe different kind of prediction strands, and I guess the dynamic is the dynamics is different in these cases. So you can see that this complete serial compound reaches the high predictive strands kind of faster. So here red, green, and blue correspond to number of trials to condition on the stimuli, and yeah, so this kind of peaks associated with complete serial compound are observed, and you can see that with microstimulus it's a bit different. We also observe this kind of peak, but only after number of trials. I'm not sure how do you interpret this, but yeah, that's something that so some results represented here. But so all right, and that's about this classical conditioning, and in this chapter, the authors associate classical conditioning and the prediction task. So if you want to add anything on it, please go on. Otherwise, we, I guess, can proceed to the instrumental conditioning and discuss its association with the control task.
Yep, let's do that.
Okay, so the instrumental conditioning is different from the classical conditioning in a way that in this case it is kind of goal directed. So essentially the kind of experiments with this instrumental conditioning, you can see this weird picture of a box. I'm not sure I understand it but whatever. So the experiments were like you construct this cage, and to open the cage, you need to do a sequence of actions. which are kind of non-obvious for an animal, and there is some food outside of a cage, so the animal wants to get out from the cage. So this experiment was done on cats, and yeah, it's probably not very nice to be a cat in this case, but yeah, as we read further, you shall see that it's better to be a cat than a rat. All right, and so the idea was the cat wants to get out from the cage. It does random stuff, and occasionally opens the box. And as number of trials increase, the cat starts to understand what to do exactly to get out from the box. So after some experiments, so at first it took around like 5 minutes to get out from the box, and later the cat managed to do it in 6 or 7 seconds. So well, essentially what this shows us is that given some experience, the animal can learn to do some things that are not obviously associated with the goal, but it can learn that well, what you need to do to achieve the goal. And yeah, so the experiment was done in late 19th century, and the found what was the product of this experiment was so-called the law of effect, I guess, and or if effect, I'm not sure. Yeah, so and this describes how we learn, and there are two properties of this law which are interesting for us. So it's selectional. So so we can associate reinforcement learning with this animal learning, as described by the law of effect. And there are two properties that kind of are common for animal learning and reinforcement learning, that it is selectional, that we try different actions, compare those actions, and compare the consequences of those actions. And it's also associative, which means that we construct this association between the actions and outcomes. So and basically that's what this number of experiments show us, that we can learn this kind of associations for actions depending on a state, and that's how the animals learn new behavior, and there are some discussions about how all this stuff works actually. So there are theories that we have some on like animals have some idea about the world, so they do not act completely at random and discover rewarding behaviors in unknown situations merely by chance, but they have some kind of picture of the world, and they try what they might think would be useful in this kind of situation. But also there is some exploratory mechanism, kind of hard-coded to the way we act, and that helps discover new behaviors in the situation we did not happen to met before. Yeah, and there are a lot of kind of concepts from psychology that are interested here. They mentioned this motivation concept, and there are experiments that show that given a stronger motivation, the enemies discovered behaviors quicker. So, for example, here they state that the cats were motivated by food to escape. So it was not only the fact that they wanted to escape the cage, but also the fact that there was a food present in outside of the cage, so they wanted to get this food. Also, there are a bunch of experiments with mazes and rats, showing that, for example, rats are finding a way to the food faster if they're hungry. So, and that makes sense. The rat is not particularly motivated to get out from the maze. It's more like motivated to find the food. And yeah, I guess that's not very surprising, but still all these discoveries were not obvious at some point, and yeah, maybe that was interesting. So another discovery that was interesting was that the following experiment was done. So the rat was placed in a maze with no food like reward, and basically no purpose. And so the rats were exploring, kind of moving around the maze without any purpose. And after some time, this reward, the food was introduced, and so the rats learned quicker to find the way to the food once they had spent after they have spent some time in the maze, as compared to the putting a rat to the maze. So that proves that essentially an animal learns the model of the environment, we can say, and that relates to the, so that's this cognitive map idea and latent learning. So the rat builds a map of a maze in the mind, although it's not yet really motivated to move to some particular location in the maze. And yeah, I guess if you think about it, it's not so surprising that I guess that is kind of hard-coded into the animals by nature, that we need to explore the world. And there are this the very similar understanding of human learning, I believe. So essentially, we as humans also have a high kind of need to predict the next state of our environment in nature, and therefore we have this kind of stress when we happen to be in a new situation that we don't know. And but on the other hand, we have this instinct to explore, and somehow those two are balanced. So we basically it turns out we both want and don't want to be in the unknown situation at the same time, in terms like we want to have a model of the world such that all the situations are predictable for us. On the other hand, we need to get into the unpredictable situations because we want to improve our model. Yeah, and that's, I guess, yet not completely understood how it is balanced in for people, and I guess for different species it can work differently, right? So let's briefly cover the last part here, this habitual versus goal-directed behaviors. So we have we have learned about model-free and model-based reinforcement learning. And just a quick reminder, so the model-based reinforcement learning is any kind of reinforcement learning when we have a model of the environment and we can use that model to make the predictions. And model-free is when we just interact with the environment directly and learn only from the actual experiences. And here the authors draw this association between habitual and goal-directed behaviors and model-free and model-based reinforcement learning correspondingly. So the habitual behavior is essentially something that we do kind of automatically, and goal-directed behavior is something that we do on purpose, and that can be thought of as planning. So an example here can be used to illustrate why having a model of environment might be useful for us. So the model-free approach would be to learn the values for each state, and this can be done only by actual interaction with the environment. And in this case, each state action pair, you can see it is associated with the reward we're gonna get. And for model based, we construct a model of the transition model of for our environment. So in this model based scenario, we know that by taking action L from state 1, we will get to state 2, and so on. And what is the benefit of having this model? So knowing that, for example, these rewards are shuffled in or permuted in particular way, we can use our model right away to get to the highest reward state. While in this model free case, once the rewards are shuffled, we need a bunch of experiments to kind of override our associated action value functions, all right? And so there is this analogy with habitual and goal-directed behavior. So these habitual behaviors are something that we do automatically. So we kind of learned that, I don't know, brushing teeth in the morning is good. So we don't have to think about, you know, I will have some interactions soon. So I rather have my teeth brushed right now and before I go out. You just do it because you kind of know that probably it's a good idea anyway. And that would be kind of something that is habitual, right? But it's not something that is built into us. We learn. So first it was goal directed. So we were kind of explained and by our parents that brushing teeth is a good idea. It's good for you for many reasons. And but after some number of repetition, the goal-directed behavior can become a habitual behavior. So that's an idea. And here in this part of the chapter, I had this, I don't know if you are familiar with this book by, what's his name? The book is called Thinking Fast and Slow. And that is system 1 and system 2 thinking, where system 1 is I'm not sure about the numbering, but one is kind of our intuitive thinking and another kind of logical thinking. And you can see that it maps nicely into this habitual and goal-directed behavior. And what the author of that book and his collaborators had discovered through experiment and confirmed through the experiments that a lot of decisions we make are done kind of intuitively, and we do not even realize that we had some decision to make. But when we encounter some more complex task, we switch to this slow kind of thinking, which is logical thinking, and then we draw this like a logical path from current state to the goal state, if you would. So yeah, and also what is argued, and I believe I've heard it multiple times, that the neural nets are essentially like an intuition this kind of intuitive thinking in human, right? And as a part of artificial intelligent system, you have this neural net that is really good as an intuitive process, and there is a question whether this slow thinking mode would arise eventually. For example, there was this like a, I don't know, an article by David Silver and Rich Sutton. So and I guess there were some other co-authors from DeepMind, and they claimed that their reward is so basically through constructing a correct reward signal, you can so that is enough to build like a artificial general intelligence. And yeah, that is kind of something to think about. I guess I'm not making good like coherent representation of the subject, but I guess you're getting what I'm talking about in general. Yeah, so I'm not an expert on all this psychology stuff, but those are my kind of some thoughts on the topic. And yeah, please share yours if you'd like.
Yep. So that was it from our side. Thank you, guys. Any thoughts or any last inputs?
If there are no inputs on the psychology and reinforcement learning, maybe someone has some results with the competitions or experiments you've tried during the week. I haven't done much myself in this regard, but if anyone has something to share, we might use some time for it, I guess.
Anybody has any results? I haven't done anything much either. And with respects to reinforcement learning, I'm a bit involved elsewhere. So
I haven't done much on the competitions this week either. I've just been looking a bit at, like OpenAI Gym. Somewhere within their gym, yeah, like they have like a sort of taxonomy of the different available reinforcement learning algorithms and stuff. I can't actually find it at the minute, but within that, they have maybe sort of like 20 different sort of reinforcement learning methods. And yeah, most of them I've never even heard of before, let alone seen them within the Sutton and Bardo book. So I
It's
think sort
within
of
the gym library, or
let's see if I can find it. I think it's no, it's maybe not within the gym. Like, I think it's just within the OpenAI. Yeah, I'll have to search for it again and publish a link up. But yeah, like so, like it divides their sort of learning algorithms into sort of model based and model free, and then below that it sort of has them all below. So you got like deep Q networks and stuff, but then you got like a load of other ones, and the vast majority I've never heard of. So
I guess it might be also useful to take time to this lectures on deep reinforcement learning. The last two lectures in the latest DeepMind course, they have two lectures on deep reinforcement learning and introduce some concepts specific to that. And yeah, I feel like there should be some middle ground between Sutton and Barto stuff and like doing more advanced, like, you know, re-implementing some research paper or like some algorithm, like state-of-the-art algorithm on something. So I guess there should be something in the middle, and yeah.
yeah, I've just found this now. So it's oh, I'm gonna get rid of. Yeah, so it's this thing is called like it's OpenAI's spinning up. It's called, and they have like this taxonomy of RL algorithms. And you can see here, so like they divide them into two, but then we're down into here. So you have like all of these ones. There's a policy gradient. We obviously covered that last week, and deep Q networks. We've done that, but then you have like all of this lot here, which I've never heard of before. And yeah, back over here, like DDPGs and A2Cs and A3Cs or whatever. So yeah, Sutton and Barto haven't or don't seem to cover this. Maybe they'll touch on that when we get to the chapter about actually sort of reinforcement learning examples in the real world.
Yeah, I guess this is kind of more on the engineering side of things. So we kind of covered the underlying like basic theory, and then there is a lot of more to do to make it really work on real world problems, right? And that's, I guess, this is what this.
Yeah. So I think we've covered the orange rectangles, maybe not onto the blue ones yet.
Yeah, so. Yeah, but that should be kind of, you know, you have the idea what's going on, and then you can you just need to implement it, play around with it. So that's probably what we should try. But yeah, it's kind of needed to find some interesting way. So what I'm thinking of doing, I want to find something that, so for me, this reinforcement learning stuff is like a hobby thing right now. So I'm not aiming to like use it really, at least like soon. And so I want to find something that would be just, you know, fun to play with. And I guess for me, it's some kind of robotics stuff. So I want to, I don't know, to make some this dummy walk or something like that. And if you have links to some nice tutorial on how to do that, I would appreciate. But I will definitely try out some stuff, and I will share the results once I have some. I guess that's my idea.
Do you actually have a robot at home that you can practice on?
No, I'm thinking about a simulator first, but actually I've bought this Arduino board, and I can kind of build a small car or something and try stuff with that. But yeah, I'm a long way from there. I need some some work to do to make to get to that. But yeah, in the long term, it would be really nice to make something that actually does stuff in physical world. Yeah, all right, so then thanks everyone for joining, and see you next week for discussion of the next chapter. And
yeah.
Okay. Cheers for that. Thanks, guys, and see you next week.
Bye.
Cheers.
Bye.
Bye.